Hello grade 12s, and I'm going to be going over the example from the kinetics lesson part 1, and I'm going to be showing you how to use the data to get to the rate law for a reaction using the method of initial rates. So to begin, we need to pull up the data from the experiments that you conducted for a given reaction. The reaction that we're going to be looking at is as follows. So here we're going to be looking at nitrogen monoxide gas and chlorine yielding nitrosyl chloride. This is a fun little element or compound. So in this reaction, we have two reactants yielding one product. So this would be a synthesis reaction. And we can see that the experiment has been conducted 4 times when we're going to be varying the concentration for the two reactants, both nitrogen monoxide and chlorine gas. So our first step is to write out the general rate law. So notice here that we have two different reactants, so we have two concentrations in our rate law. We have our exponent x and our exponent y, so we need to determine these two values. And we're going to be using, like I said, the initial rate method. So to do this, we're going to be looking at the changing concentration of one reactant while the other is being held constant, and then we're looking at the rate and seeing how that changes as well and how that's affecting our exponent. So the first one we're going to look at is the nitrogen monoxide. So for us to look at nitrogen monoxide and see how that affects the rate of reaction, we need to hold chlorine gas constant. So chlorine gas is being held constant in two experiments, so in trial 1 and trial 2, experiment 1 and 2, as well as trial 3 and 4. Let's go with the first two. We can see it's being doubled, the concentration of nitrogen monoxide, and then we're going to be using these two values as well. So we're going to have the concentration of nitrogen monoxide in trial or experiment 2 divided by the concentration of nitrogen monoxide in trial or experiment 1 raised to the exponent of x, because that's what we see in our formula. And this is going to be equal to the rate divided by the rate from the second reaction divided by the rate from the first reaction. So now we're going to substitute in those pieces of information. So to get the concentration in the second experiment, we're using this value here. I'll just put a line under it. So we can substitute that value in. So we're going to have 0.500. And then our concentration in the first reaction for nitrogen monoxide is 0.25. And this is raised to the exponent of x. And then for our rates, we're going to be using these two values. This is our rate in our second. For our second R2 value in our experiment number 2, it's going to be 5.72 times 10 to the negative 6 divided by the rate from our first reaction, which is that value there, the 1.43 times 10 to the negative 6. So we can reduce this side of the equation further and also solve for this value as well. So we end up with 2 to the x is equal to, this equals 4. We know that 2 to the exponent of 2 gives us a value of 4. So that indicates that x will be equal to 4. And so when we go to so we can say now that x is going to be 2, so we can substitute that into our formula here. So now we need to figure out our y exponent. We need to figure out what this value is. To determine this, we need to hold our concentration of nitrogen monoxide constant. So we want to use an experiment, either experiments 1 and 3 or 2 and 4, because the concentration is being held constant. So let's try going ahead with, we'll do 1 and 4, or sorry, 1 and 3. So I'll write the formula down. So here we're going to have the concentration of our chlorine gas in trial 3 divided by chlorine gas concentration in trial 1, raised to the exponent of y, because that's the exponent we're looking for, is going to be equal to our third experiment's rate divided by our first experiment's rate. I will substitute in the values that we see from above here. So our concentration of chlorine gas in our second experiment is 0.500, and in our first experiment it was 250. So this is all raised to the exponent y, and then we have our in our third experiment's rate, we have 2.86 times 10 to the negative 6, and we're dividing by that rate from our first experiment. So we have 1.43 times 10 to the negative 6. 10 to the negative 6. So now we can solve for both sides. So we end up with 2 to the y is equal to 2. We know that this exponent, that 2 to the exponent of 1 gives us 2. So this y will be equal to 1. So now we're ready to go back up to our general rate law and exchange the value for our y. So I'm going to do that. Now we need to solve for this k constant. To determine the k constant, we want to use one line of the experiment. So I'm going to get rid of this information and we're going to solve for that k. So for this part, I would like us to use the first experiment. So we're going to substitute in the values that we see for this experiment up here. So we're going to put in the concentration of nitrogen monoxide gas as 0.25, same with 0.25 concentration for our chlorine. So we will substitute in those pieces of information. K is what we're solving for, and our rate is given right here. So we're going to substitute in those values right now. Okay, so now we're ready to combine. We can combine these two numbers here because they are the same value. So 0.25 raised to the exponent 2 times 0.25 is the same thing as 0.25 raised to the exponent of 3. So now we want to isolate our k value. To do this, we want to do the opposite of what operation is currently occurring to the k. We're multiplying by 0.25 raised to the third. So we want to do the opposite and divide by 0.25 raised to the third on both sides. So what I've done here is now I'm going to just pull out the units. So we have, for our k value, if you look at our data here, our unit for k is moles per liter per second. So I'm just going to write that down, moles per liter per second. And so the next thing we need to consider is we're dividing by. So when you divide by something, you're basically doing the inverse. So we know that molarity is moles per liter. So if we're inverting that, we're going to have liters on top, but we've cubed it. So we need to make sure we have the cube. So we have liters on the top and it's cubed, and moles is on the bottom. Sorry, these m's should be mole. So now we're at a point where we can evaluate this with our calculator, and then I'm going to show you afterwards how to reduce and figure out our unit for k. So we end up with a value of 9.15 times 10 to the negative 5. And now to get rid of, or to reduce our units, mole divided by mole cubed will end up, we could cross these off because this will actually reduce our mole to being 2 on the denominator. For our liters, liter cubed divided by liter, this is going to reduce our liters to be squared on the numerator. So we're going to end up with liters squared divided by seconds times molarity squared. And this will be the value of our k. So our next step is to write down our rate law and put in the value for k as well as our values for our x and our y. So this will be our final rate law equation.